All right, good afternoon. I'm excited to share a little bit today about Tripadvisor and how we've been making use of Ray and Anyscale. My name is DeStories. I'm an ML engineer at Tripadvisor, and day-to-day I'm focused mostly on search and generative AI. I'm joined by Sam Jenkins on our machine learning platform team, who owns much of the work around making Ray really broadly accessible and easy to use across our organization. Before we get into details about Ray, I first want to touch on the kinds of business problems that we're ultimately trying to solve. So hope many of the people in the crowd here have used Tripadvisor before, but you may know that we have a very broad array of product surfaces that span the full traveler journey, from discovery and travel inspiration to more detailed trip planning and interactive generative AI experiences, all the way down to lower funnel shopping, price comparison, and booking for hotels, restaurants, attractions, tours, tickets, and more. And in order to provide the best possible user experience, we have AI and machine learning integrated across all of these surfaces. That includes things like real-time AI agents, recommender systems, search and information retrieval, computer vision models, sort, and more. We have hundreds of offline machine learning workloads, hundreds of real-time ML models being inferenced, and a very rapidly growing number of AI microservices that are doing more complex orchestration of things like agents. These are also operating at fairly large scale. We have models inferencing over hundreds of millions of user reviews, hundreds of millions of user-uploaded photos, billions of users, and millions of locations. And so in order to make all of that possible, we have a very comprehensive machine learning platform. This slide shows a snapshot of what our ML ecosystem looked like as of last year. And it's a mix of both open source technologies as well as some proprietary software that we've built out. So on the offline side, we have a centralized job scheduler as well as lightweight workflow orchestrator, which is built around Netflix Genie. For machine learning workloads in particular, we primarily use that scheduler in order to trigger Kubeflow pipelines. And Kubeflow pipelines run in Kubernetes, and they allow us to containerize and then schedule Python tasks on arbitrary hardware by leveraging Kubernetes primitives like affinities and tolerations. We use Snowflake as our centralized data lakehouse for all of our analytical usage of tabular data, including for machine learning. And then even as of last year, we had some fledgling use cases for Ray, in particular using Ray data within a task of a Kubeflow pipeline. So running in single node cluster mode, and then using that for things like batch ML model inference, as well as data ingestion to our vector database. On the real-time side, we use Selden Core and Selden ML Server for inferencing of real-time models, Fast API for implementing AI microservices with those more complex orchestration logic. We've built out a proprietary feature store, which supports both real-time and offline reproduction of features. In the real-time case, we use Valkey for fast key value retrieval of static data, which is usually updated periodically on a cadence like once every day or maybe a few times a day. And then ScyllaDB for near real-time updates of user interactions data. So think, what are users browsing or clicking on Tripadvisor when we want to feed that into our models. We also use Quadrant as our vector database for high-performance retrieval over very large high cardinality data sets, so things like our user reviews, our forum posts, and other information about locations. And then if we fast forward to 2025, really the biggest shift in our ML ecosystem has been a broadening of our adoption of Ray. What that's looked like is moving beyond single node Ray to clusters of auto-scaling multiple heterogeneous compute nodes. We've also been decoupling Ray from Kubeflow. So we're not just running within Kubeflow pipeline tasks. we're running Ray jobs independently. And this is made possible by Anyscale platform. In addition to that, we're also starting to look at Ray, not just for offline workloads, but also for real-time AI applications as an alternative to these independent deployments of fast API services plus Selden ML server model deployments. So why invest more in Ray? I'd like to start by kind of laying out the conceptual shift that Ray and its abstractions allow us to make versus our existing infrastructure. On the offline side of things, we see Ray jobs primarily as an alternative to Kubeflow pipelines, which is kind of interesting actually because Kubeflow pipelines and Ray jobs aren't quite the same category of infrastructure. Kubeflow is a workflow orchestrator, whereas Ray is a compute framework. And so what that kind of means when we go to operationalize some workload for production is that with Kubeflow, that amounts to breaking down the workload into individual tasks, containerizing those tasks, and then scheduling them into a DAG. When we do that, we then have to delineate the tasks along the lines of the compute that they require, because Kubeflow has this tight coupling between the implementation of the task, the container that it runs on, and the compute that it gets scheduled on. And so that's a little bit rigid, and it introduces a bit more boilerplate than we would like. With Ray jobs, on the other hand, we can control both horizontal and vertical scaling of any portion of our workload inline in the Python code itself. So it's fairly flexible. It is also a lot more concise, and so we end up with much smaller jobs that are more maintainable, easier to write, and it turns out a bit more efficient as well. And we'll see more details on that in a couple slides. On the online side, for real-time inference and services, we've seen a pretty big shift in the past few years where the scope of work that a machine learning practitioner has to do has expanded considerably. It used to be that machine learning scientists and engineers would spend the bulk of their time training and deploying individual models, and then those model deployments would be passed off to separate dedicated software engineering teams who would manage business logic and orchestration of when and how to inference those models. But what we've really seen emerge increasingly, and especially with the rise in popularity of generative AI agents and the demand for more sophisticated search systems, is a need for very often the very same developer to be able to both train and deploy models, but also implement the microservice logic that controls how to inference those alongside things like LLM APIs, vector database retrieval, feature service lookups, or calls to other microservices. And that's often happening in kind of complex and non-deterministic ways. So that's where Ray Serve comes into play for us as very interesting as an abstraction, given that Ray Serve really supports not just deploying machine learning models, but consolidated machine learning applications, including both that orchestration logic as well as the corresponding embedded inference. So that's kind of the intuition behind why we thought Ray was interesting. But to get past intuition to some more concrete numbers, in Q1 of this year, we ran a proof of concept in which we implemented several use cases with Anyscale platform in order to draw comparisons back to Kubeflow pipelines and then fast API and ML server. We implemented one of our real-time AI services, which powers a location search use case for many of our AI products. This is performing hybrid semantic and lexical retrieval over our various location types along with their associated reviews, and then re-ranking in order to provide the best possible recommendations for a user query. We implemented two of our batch embedding pipelines for images and reviews. We implemented a kind of interesting pipeline called AI collections, which actually wraps up all of the logic of a real-time service and then inferences it over millions of inputs in batch, so we can kind of have a single implementation double as both a real-time service and a batch pipeline. In this case, that amounted to demonstrating that we could take a Ray Serve application and scale it within an ephemeral cluster as part of a Ray job being inferenced as a UDF within a Ray data pipeline. And then finally, we did some benchmarking of LLM batch inference using Ray data and VLLM to compare against some of the managed offerings that we have available at Tripadvisor, in particular Together AI APIs and Snowflake Cortex. What we saw from the proof of concept were some pretty staggering results. One of the big ones, particularly for me as a machine learning developer, is the reduction in number of lines of code. For these batch use cases, we saw over 80% reduction in number of lines of Python in order to implement the same logic. We also saw some really huge drop in cost corresponding to better utilization of our compute. So over 80% drop in cost for things like image embeddings and review embeddings. Those cost savings also translated when we compared against API offerings for LLM batch inference. We saw similar improvements for real-time use cases as well, with large reductions in latency compared with ML server, as well as increased throughput on the same hardware using Ray serve rather than ML server. So all these results clearly were very promising for us and inspired us to invest more in making Ray very accessible and use it in more of our use cases, which led us to a decision of should we build out platform support around Ray open source, in particular KubeRay, or should we procure and integrate Anyscale as a managed platform? Now at Tripadvisor, we love free open source software, and KubeRay in particular was a very appealing option to us because our team has many years of deep expertise in maintaining systems on Kubernetes. Open source is also great because you have a lot of flexibility in order to implement things exactly according to your own requirements. But on the other side, Anyscale provides very polished and very developer-friendly experience out of the box with a number of really nice enterprise-friendly features that help improve reliability of jobs and services, manage governance, and optimize performance and cost of our workloads. The single biggest deciding factor here, though, was actually the opportunity cost of building out our own platform support versus getting something off the shelf. We'd originally estimated that it would take us about 7 to 10 months of platform engineering time in order to get to a point where we could really scale up our adoption of Ray across the organization and run workloads in production. And that's not only quite a bit of engineering effort where our platform engineers have many other very valuable things that they could be working on, but it's also time spent where we wouldn't be able to take advantage of some of those kind of order of magnitude improvements that we saw on the last slide. Things like developer efficiency and compute efficiency of the machine learning workloads that we're building. And so for those reasons, we decided to move forward with Anyscale. And now I'd pass it off to Sam, who will walk us through our journey in integrating Anyscale platform with the rest of our ecosystem.
Great, thank you, Jay. I'm Sam Jenkins. I work on the machine learning platform team here at Tripadvisor. I support our data scientists and machine learning engineering teams on taking their research through to production. I'm also the technical lead for the integration of the Anyscale platform with our existing machine learning infrastructure and tooling. So as part of my section here, I'm going to talk about how we've integrated Anyscale with our existing platform, so building on the proof of concept that Jay just spoke about. I'm going to go into detail on our production batch workloads on Anyscale and the performance improvements that we've seen. We're also quite early on in our adoption, so I'd like to touch on some of the exciting things we're working on now and the things we're going to do in the future as well. So, as you'd expect from a mature MLOps platform, a very data-driven company like Tripadvisor, we have a lot of existing infrastructure and tooling supporting our machine learning use cases. So we needed to consider some key areas in our integration. So we have a number of AWS accounts supporting our back office and services use cases for offline and online workloads, respectively. We have a number of orchestration tools dealing with anything DAG-based, so anywhere from your more traditional data ETL tooling to model training and deployment pipelines as well. We have a significant amount of internal tooling, so anywhere from our MLflow model artifactory to our in-house feature store, vector databases, S3 buckets, internal Python libraries. We also have what we call our developer workflow, so how do we actually make this system easy to use for the end user? How do we abstract that platform detail away so the data scientists can do what they do best? We also built integration with our monitoring and observability stack on Prometheus and Grafana as well. So how can we show value from this integration? So to talk in a little bit more detail about the infrastructure and MLOps setup. So as I said, we have 2 back office AWS accounts, one sandbox for infrastructure testing and changes, and a production account as well for the offline workloads on Kubeflow. That gave us a logical separation for the Anyscale clouds, wrapping the AWS infrastructure that we have. So we have one sandbox Anyscale cloud and one production Anyscale cloud. These are divided into a number of Anyscale projects, which are separated by data science domain. So a domain is areas of work, such as image data science or text data science. So we have a development and a production project for each of those. Dev supports the active development of our jobs and services, and then the production in the back office accounts run the deployed jobs. Services are then deployed in the services Anyscale clouds through a CI/CD process as we need to support live traffic on those accounts. We also utilize Anyscale's project-scoped IAM roles, which allows us to operate on the principle of least permissions in AWS as well. So we deal with a lot of personally identifiable information. So this means we can finally scope our projects to the people who are allowed access to that as well. So to talk in a bit more depth about our developer workflow then, and how we made this system easy to use. For job development, Anyscale tooling really makes this quite simple. So you get simple access to the head nodes of clusters, which easily allows our users to quickly iterate their workspaces, jobs, and services. We set up CI/CD pipelines to package up our jobs for orchestration. We use semantic versions, conventional commits for automated release notes. We have custom image builds to package up our dependencies. We also have isolated job runners to deploy our jobs as well. For role-based access control, we have Azure Active Directory, which syncs to our projects as well as the Anyscale project IAM mapping that I spoke about. Interestingly, we kind of built a in-house GitOps tool as well for our project management. We built this on top of the quite fully featured Anyscale API, and it allows us to have a Git repo that controls budgets and alerts for our projects, user access control, importantly, compute configuration, so users can raise PRs if they want to use new GPUs, and MLOps can say, no, that's too expensive, or yes, that's great for your use case. This also has the added benefit of disaster recovery as well. So Anyscale clouds, if you need to change some configuration, you often need to bring them down and back up again. So this really allows us to just bring back our projects very quickly. So to talk about some of the differences that we've seen between our Anyscale setup and our Kubeflow setup then. Hardware flexibility and resource utilization in Ray. So Ray scheduling these heterogeneous workloads is something we couldn't really do easily on Kubeflow. So we get mixes of CPU, GPU, and memory-intensive workloads. We also see much reduced idle time from our Kubernetes resources as well. The spot instance proactive interruption handling is very useful for us in terms of managing cost and maintaining that cluster state if spot instances drop down and an on-demand instance comes back up. The simplified developer experience can't really be understated compared to Kubeflow. So there's no need for our end users to understand or even remotely deal with Kubernetes primitives. You can just write Python, which makes this much easier to go from research to production and easier to debug. The operational observability is really good as well. So Ray dashboards make for easier optimization, and you've got the proprietary Anyscale data dashboards as well in there. And it's really a unified platform. So allowing a developer to develop test batch jobs and online inference and services directly from one cluster, from one workspace, and then run that in production is a really useful feature. So I'd like to talk about some of the production batch pipelines that we've migrated so far from Kubeflow to Anyscale. I've got 4 examples to discuss across the image data science domain and locations data science domains. So to start with our image processing, so we have 2 pipelines here, one standard batch inference pipeline, another quality scores pipeline. So the embeddings pipeline computes and stores embeddings for all images that are published to Tripadvisor, so it's very important. They're key components that fuel downstream pipelines and on-site use cases, so primary photo selection and media gallery albums. So the nice picture of our monkey here was likely scored highly through one of our models, I would say. This runs on a daily cadence with around 100,000 images per day, but if we make changes, for instance, to the embeddings model, we run backfills on all 400 million images that we've got at Tripadvisor. We use an open source Google Vision Transformer model for this as well. So our quality pipeline is similar structure to embeddings in that it's a batch inference pipeline, but we use 2 models here, one for aesthetics and one for technical quality scoring. So the aesthetic score model uses an open source visual and language assistant model from Google, which learned aesthetic preferences from human ratings to predict how visually appealing an image is. So as part of this pipeline, images are resized, encoded, and scored, and those raw outputs are normalized for the output as well. The quality score uses another Google open source model, which was trained to assess the technical image quality, so sharpness, noise, compression artifacts, etc. So images are center cropped, encoded as JPEGs, scored, raw outputs are normalized, and then we store the scores. So to talk about the performance improvements that we've seen building on the proof of concept examples. So we have Kubeflow on the left here as our baseline at 100%, and then Anyscale on the right. We measured across wall clock time, compute cost, lines of code. Lower is better. So particularly beneficial for these pipelines is Ray Data's streaming workloads to decouple the CPU-based Ray actors for image downloading and pre-processing, etc., and the GPU-accelerated Ray actors for the actual embeddings process itself. So we see that utilization is higher on Ray than running on Kubeflow for the equivalent pipeline, and resulting in a 65% reduction in clock time for this. And we see an associated drop in costs, largely due to the efficiency gains from the hardware utilization and reduction in overheads as well there. Again, the developer experience is much smoother. Reduction in boilerplate code with these native Python frameworks means we've dropped the lines of code for this job for about 87%. So moving on to our locations data science domain. Our location embeddings pipeline generates embeddings again through combining names, descriptions, popular mentions, known for keywords, and tags. And we use this for semantic and lexical search, so we produce sparse and dense vectors accordingly here. We process 12 million points of interest in total, processed per quarter, and 1 million per day incrementally. The interesting thing about this pipeline is that we initially ran this on Kubeflow with open source Ray on single node. So similar improvements on the performance across our metrics here. The dynamic CPU and GPU mixing, again, wasn't something easily that we could do with KubeRay, with the open source. So it was easy for us to do this on the Anyscale platform. We also employed the proprietary Ray Data Snowflake connectors for utilizing the object store efficiencies here across the cluster for loading and writing text as well. So another pipeline here is our geolocations embeddings pipeline, which combines geos and location features as embeddings here. So we use names, latitude, longitudes, descriptions, popular mentions, known for keywords and tags. And these embeddings are used by our re-ranker and recommendation models to output personalized points of interest. This processes 220,000 geolocations, which gives us 100% coverage across Tripadvisor. This is a net new pipeline, so I thought it would be good to talk through the process at a high level here. So we load from Snowflake our geo descriptions, known fors, product themes, tags, and keywords. We do some joining and aggregation here to produce name hierarchies. So Paris, which is in France, which is in Europe, as a hierarchy there. and a series of metadata text as well. We then use Ray Data's map batches to produce name embeddings here, using an open source general text embeddings multilingual model, as well as a general text embeddings model for the metadata as well, which outputs our hierarchical name vectors, our location name vectors, and our rich contextual vectors for the search downstream. We load that back into a Snowflake table for use downstream as well. So we're fairly early on in our adoption as of this year, so I wanted to talk a little bit in this final slide about our future work and plans. So in our future exploration, we're looking at agents on RayServe, as well as LLM training and fine-tuning. We're also looking at LoRa on RayServe as well. If we could train multiple LoRa adapters and host them on top of one LLM, that would be useful for some of our use cases. We're looking at MCP servers, as well as knowledge distillation as well for efficient inference. We're also working on our full migration to Anyscale, as it kind of forms the backbone for compute in our MLOps stack. So we're migrating the existing offline feature store library to Ray Data, which we currently run on Spark on Kubernetes. And we're already seeing some quite dramatic performance improvements from moving away from that system. We're migrating our Fast API microservice framework to Anyscale services. I've presented 4 pipelines here, but we have many more batch processing pipelines that we want to move across, as well as our classic machine learning model retraining pipelines as well. And yeah, that is it from me. And I think we've got a couple of minutes left for some questions, if anyone has any. Thank you.
Hi there. Just one question on the reduction in, I think you have a chart where you have a before and after, and you get like 50% improvement. Just want to know if you are using the same amount of hardware, because I think your before is 1 node, but after, are you using more than one, like accelerator or something?
More than one what, sorry?
Hardware, like are you using the same amount of hardware here?
Yeah, it's the same type of hardware, but we are able to elastically scale our GPUs across and CPUs across more nodes.
Got it. I see. Thank you.
Yeah.
The cost here is also reflecting that, the cost of each node. So that reflects that it's running more efficiently and not just scaled up more horizontally.
Yeah, thanks.
Thank you for the talk. As you guys approach this migration, like, how have you guys planned this in terms of like making sure it does not disrupt your current operations versus also making sure you get to the new platform as soon as possible? So how has that been planned for you guys?
Sorry, I missed a bit of that. Did you say?
As you guys migrate to Anyscale,
yep.
How have you guys tried to manage this, maintaining your current operation versus looking forward?
Yeah, that's a good question, actually. So we initially brought on some of our machine learning engineers as opposed to our data scientists who were more familiar with the platform aspects. So that made it a kind of easier migration in terms of, right, these guys understand the infrastructure side in a little bit more depth, the hardware side in a little bit more depth. So we could give them a bit more freedom to kind of play around and bring that on. Once we set up our tooling, our CI/CD pipelines, and our processes for deploying jobs and services, we started to bring the data scientists on as well. So we kind of had a phased adoption, and we're still going through that phased adoption as well. Great. Thanks a lot, everyone.